Okay, in the last lecture we saw at least 4 problems for which I said the best known algorithms take exponential time. Okay. Now, but there is something interesting about these problems that I can suppose, which we will see this lecture. Suppose the max click problem has a polynomial time algorithm. Right? It's a major open problem. We still don't know. The best known has an exponential time algorithm, but suppose there is somebody comes up with a polynomial time algorithm to determine if a given graph on n vertices, what is the size of the maximum subset of vertices which are mutually adjacent. Okay. Then what are some consequences? Now, so I am going to show a couple of consequences. One is that max independent set problem has a polynomial time algorithm. It turns out I can use, let us call this algorithm as A for CLIQUE. An algorithm which takes as input a graph and takes some n square, n cubed, n power 4, some n power constant time and comes back and says, here is the maximum click. Can I use it as a black box somehow to solve my other problem, which is the maximum independent set problem, where I am given a graph, I want to find a maximum size subset which are mutually non-adjacent, and it turns out you can. Think about it, right? It's not on the same graph we are looking at. Remember, both of these problems take an arbitrary input graph and they are supposed to come up with an answer about the max click or max independent set. Now, suppose max click has an algorithm A click, let us call it. I want to tell you now that maximum independent set problem can be solved in polynomial time. Well, what is the input to the maximum independent set? Okay, I am going to give you a proof of this, right? It's a graph G with the vertex set and edge set, right? I am given this graph G and I am interested in the maximum subset of vertices which are mutually non-adjacent. That is my goal. And I am telling you that the best known currently has an exponential time algorithm. But suppose somebody gives me a max click algorithm as a black box, can I use it? Turns out yes. So, what do? I somehow, okay, so here is my max click algorithm, which will take some graph and give you a max click. To max click algorithm, I am going to give the complement of G. Okay. This is again one of basic operation on a graph. Basically, take your graph, whenever there is an edge in the graph, remove that edge. Whenever there is no edge in the graph, put an edge, and that is called the complement of G, right. So, if this is my graph, G complement would be on the same vertex set. 1 2 is an edge, so 1 2 will not be an edge here. 1 3 is a non-edge, so here it will be an edge, because 1 3 there was no edge. 2 4 there will be an edge here. 1 4 is an edge here, so I will not have an edge. So, that is it. This complement will have only this missing edges 1 3 and 2 4. Okay, so it's a, think about, if I give you a graph in the form of an adjacency matrix, how much time do you need to get G complement. It's a very easy question. You can do it in polynomial time. It's very easy. I mean, in square time. Okay. How do I, given the graph, let us say in the form of an adjacency matrix, how do I get the complement? Okay. So, this is an exercise. Very easy exercise. Think about it. So, now what I am going to do is compute the complement. I know it is doable in polynomial time, even in n square time, and give that complement to my CLIQUE algorithm. CLIQUE algorithm will output some S. S, the word is S induces a clique. That is a technical term, which means that there is an edge between every pair of vertices in S. So, CLIQUE algorithm is supposed to take some graph. In this case, I am going to take the complement of my input graph, give it a CLIQUE algorithm. CLIQUE algorithm comes up with some subset of vertices where there is an edge between every pair of vertices. So, now very easy claim is that S induces a clique in G complement if and only if S induces an independent set in G, right, because by the definition of the complement, if you have this S, there is an edge between every pair of vertices in this complement graph, then if you go back to the original graph, there will not be any edge at all between any pair of vertices in that graph. So, that will be induce an independent set. Conversely, if you have an independent set here in the complement graph, there will be an edge. So, the CLIQUE algorithm will actually, when it gives you the maximum clique in the complement graph, which will be the maximum independent set in the original graph. Okay. So, if I want to find a maximum independent set in a graph, I just simply find the complement. How do I find it? In square time. How? Exercise. And then take the complement graph, give it to my CLIQUE algorithm and say, give me the max clique here, and whatever answer it gives, that same subset induces the maximum independent set in the original graph. So, we have solved maximum independent set problem in polynomial time. First observation, that is easy. Second observation here, this is much more interesting, is that SAT can be solved in polynomial time. Simply because you are managing to solve max clique in polynomial time, this is interesting because SAT is a problem in some sort of a logic, whereas CLIQUE is a problem in graphs, but somehow I have an algorithm, a CLIQUE algorithm can be used to solve SAT in polynomial time. Let us see how. Okay. This is a slightly non-trivial, what we call a reduction. So, what is the input to the SAT? I am given this variables x1 to xn and clauses c1 to cm. What I am going to do is to use a CLIQUE algorithm. A CLIQUE algorithm requires a graph. So, from this SAT instance, I am going to construct a graph, use the a CLIQUE algorithm, which will give me the max clique. Somehow from there, I am going to answer the question, is the formula satisfiable? Can I satisfy all clauses simultaneously? That is our question. Remember? Yeah. So, what I am going to do, the graph, we will construct a graph. Graph means it should have vertices and edges. So, what the graph is going to look like is that it is going to have a set of vertices one corresponding to each of the clauses, right. V, a set of vertices V is actually going to be, let us call this VC1 union VC2 union blah 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 VCM, where VCI corresponds, it is a subset of vertices that corresponds to the clause CI. And what does it contain? Whatever number of literals you have in C1, I will have that many vertices in CI. So, if your C2, let us see, is x3 bar or x5 bar or x7 or x8, then my C2 will have x3 bar, x5 bar, x7 and x8. Okay. So, there is a vertex corresponding to every literal in every clause. So, this is my vertex set. I have told you vertex set. Okay. These vertices are labeled by the literal in the clauses. Now, I am going to tell you the edge. Okay. That is my vertex set. E, okay. I have some xi in Cj is adjacent to some xk in Cl, right. So, there is an xi here and there is an xj here or xk. Xi and xk are here. I am going to add an edge between these two if the following is true. J is not equal to L, these two must be in different clauses. That means, in the same set I am not adding any edge. So, each Ci is an independent set and Xi is not equal to Xk bar. One is not the complement of the other. Okay. If such a case, then I will add an edge. So, I have told you the entire graph corresponding to my formula. My formula has a bunch of clauses. So, for each clause I will have a set of vertices. Each vertex has a label corresponding to that specific literal, and then I draw an edge, no edge within a clause, within a set corresponding to a clause. The edges are only across, and if I have an edge, some literal in one clause and some literal in other clause, I will draw an edge, all possible edges, as long as one is not the complement of the other. Okay, that is it. I have defined you a graph now. I have defined you a graph. Okay, from the formula I have defined you a graph. Now, I give this graph to my CLIQUE, which is supposed to find the max clique size. The claim is, this is an interesting claim, and you are going to have f which is equal to C1 and C2 and Cm is satisfiable if and only if this graph I have constructed has an m clique, a clique of size m, right. I give it to my CLIQUE algorithm. If it comes back with a clique on m vertices, then I know that the original formula is satisfiable. The max clique size is smaller than m, then I know it is not satisfiable. Why? I am going to prove this claim. Because of this claim, I can use the CLIQUE algorithm to find the max clique in the graph. From the answer, I can check whether my given formula is satisfiable or not. Let us see how to prove this, right. It is a very short proof and then we will stop. Well, not, yeah. Suppose f is satisfiable. First of all, let us just look at this graph. What is the maximum size of a clique even possible? Can you get a clique on size more than m? No, because if you have a clique on size more than m, it must pick two vertices from the same CI set, but there each CI is an independent set, there are no edges. So, you cannot have a clique of size more than m. So, the maximum you can get is m, and any max clique of size m should pick one from each of the clauses. Okay. Good. So, suppose f is satisfiable, that means what? C1, C2, Cm, that means there exists values to 0 1 values to xi's such that each Ci is satisfied by that assignment. Okay, so suppose C1 is satisfied by this literal, whatever that literal is in that assignment. C2 is maybe satisfied by this, C3 is satisfied by this, and Cm is satisfied by something here. Then I claim this set of vertices form a clique. So, the claim is that the corresponding set of vertices is mutually pairwise adjacent. Okay. Why? So, I want to claim that every pair there is an edge. Okay. Well, remember I have picked these vertices from different clauses, so no problem. When will I not have an edge? If it so happens that this was some xi and this happened to be xi bar, then I will not have an edge. No, but that is not possible, because why did I pick this variable here? Because it satisfied this clause, which means it was set to true. Then the x bar would have been false. So, how can you say that in this clause this is satisfying it? No, in each clause you picked a literal that was set to true. So, it is not possible that I picked xi from one class and xi bar from another class, because one of them will be false. So, I have picked true literals from each of these clauses. So, it is not possible there is an xi in one class and xi bar in other class. So, there will be an edge between every pair of vertices. Okay. So, that means they form a clique. So, if it is satisfiable, then there is an M clique. That is one direction we have shown. The converse, if there is an M clique, it is the same argument, then the clique has exactly one vertex from each Ci, set the corresponding literal true. To satisfy my formula, right. Essentially, the forward direction can be simulated on the converse also. Suppose you have an M clique, because each set is independent, there cannot be two from each clause. So, there must be exactly one from each clique, each set corresponding to each clause. Collect now, that corresponds to a literal. I am saying go and set that literal to true, then you will satisfy each of these clauses, right. Because there is no conflict, because it is not saying set this literal to true for one class and then set it the same thing to false in another class will not happen. That will happen only if you have an xi here and xi bar here. But if they are there, then there cannot be an edge, but you started with the CLIQUE. So there is an edge between every pair of them. So you cannot have an xi in one set and xi bar in another set. So you can safely set each of those literals to true and you can satisfy my original formula. Okay, good. So what have we shown is that I gave you a list of 4 problems for which I said the best known algorithms have exponential time algorithms, but, right, best known are exponential time. However, they are related, at least some of them are related in some sense, that if I have a polynomial time algorithm for one problem, I can use it to give a polynomial time algorithm for a couple of other problems. This kind of relation is very useful and it is called a polynomial reduction, and we are going to somehow show in the next lecture that there is this whole class of problems which is, we will give some formal definitions of what is P, NP, NP hard, that they are somehow inherently related, thousands of problems, in the sense that a polynomial time algorithm for one will give a polynomial time algorithm for the other, but as of now nobody knows a polynomial time algorithm for any of them. So it is widely believed that all of these problems are inherently hard. Okay. So this is the notion of NP hardness, which is used to show a problem is hard. You don't expect a polynomial time algorithm, okay, but it's still not settled. It's a $1 million open problem. So we'll talk about all these terminologies and use these reductions to come up with some big framework of problems that are hard. Okay, that's for next lecture. Thank you.